Hey everyone, this is Dr. Walker. This is example number 2 from v578 on Ampere's law. In this example, we're going to find a magnetic field inside and outside a wire that has a non-uniform current density, unlike the previous example where the current density was uniform. So in this example, the current density is given by 2br cubed. Let's take a look at the case where we are looking outside the wire, r greater or equal to r, and let's write down Ampere's law, the line integral of b dot ds equals mu naught I penetrating that surface made with that by that Amperean loop. So when we are outside the wire, we're going to pick a circular Amperean loop, and it's going to work just like the other examples. The magnetic field is parallel to ds at all times, and it's constant. So the dot product vanishes, the b comes out of the integral, and the line integral of ds is along the circumference of this Amperean loop that we have chosen, and it's going to be 2 pi r since this loop has a radius of r. And we still need to figure out mu naught I enclosed, right? I penetrating this surface. So remember when we used Gauss's law and we're trying to find Q in over epsilon naught, and when the charge was not uniformly distributed, do you remember what we did to find the charge enclosed? We did the integral of rho dv. I know it's been a while, but that's how we found the charge, the integral of rho dv. Well, when the current density is not uniform, to find a current, we do the integral of the current density dot dA. And I did introduce this equation in video 541. We didn't do any examples using it, but that's because I knew we were going to use it at this point. So the current density is not uniform. It integrates J dot dA to find the current. All right, so again, going back to this just so that you can remember a little bit, if we had a charge density, even if it was non-uniform, if we were trying to find the field outside, then when we integrated, we didn't integrate from 0 to r, right, for a Gaussian surface r, because the charge only went up to a radius capital R. So when we were outside our charge distribution, we integrated from 0 to r, because the charge was confined to that space. Same thing here. When we're trying to find the total current enclosed in this Amperean loop, we're going to integrate from 0 to capital R because that's how big the wire is. So we're going to go from 0 to R. Well, but we need to rewrite this as well here. So let me put b 2 pi r mu naught. Let's go ahead and write down what J is 2br cubed, and what is dA? When we did dV, it was 4 pi r squared dr, but whenever we have a dA, we are talking about the area of our loop. And so the area, well, what we do is we break the area of this loop here into very, very thin little strips or little loops, right, that have a width dr, and we integrate over the whole radius, and it's the circumference. To make a long story short here, the dA was 2 pi r dr. Hopefully you remember this. And now we can put our limits. They're going to go from 0 to r in this case. Let's go ahead and simplify. b 2 pi r. Let's take out the 2 pi b, sorry, 4 pi b out of the integral. So we have the integral from 0 to capital R of r fourth dr. And that's going to give us 4 pi b mu naught. It's going to be r to the fifth over 5. And we're going to take the limit of capital R. So capital R to the fifth over 5 is going to be this integral, since we have 0 here as the lower limit. And now we are ready to solve for B, the magnitude of the field outside this wire. We can cancel out 2 pi. Here, make this a 2. We can cancel out, oh, that's the only thing we can cancel out. So we're going to be left with 2b mu naught r to the capital R to the fifth over 5 little r. So this is the field outside of this wire. Hopefully you see the similarities with using Gauss's law, and this is a familiar process. Now let's look at the case where r is smaller than the radius. It's going to be very similar. We can write Ampere's law again, but it's going to simplify very, very similarly. The only difference is going to be at this third step here, where if we have picked an Amperian loop inside the wire that has a radius of little r, then we're trying to find the current going through this little loop here. We're only going to integrate from 0 to little r. So I'm going to go ahead and skip to this third step. It's going to be b 2 pi r equals, actually I can skip to this step here. It's going to be 4 pi b mu naught. The integral is going to go from 0 to little r instead of 0 to capital R. And since we don't like these r's to be the same, we can just put a prime here. And now this is going to give us r fifth to the fifth. So we have 4 pi b mu naught little r fifth to the fifth over 5. And now we can divide by 2 pi r. We're going to cancel out 2 pi, make that 2, and this time we're going to cancel out one of the r's here. So our final answer for the magnitude of the field inside the wire at a distance r away from that central axis is going to be 2b mu naught little r to the fourth all over 5. In the next few videos, we'll see that we can also use Ampere's loop when our wire makes loops, such as in solenoids.